So I'll start by thanking the organizers, although I'm not sure thanks is the right word, having had to prepare 3 lectures for this meeting, but nonetheless, I will thank the organizers for giving me this opportunity to tell you about some of the work we've been doing to explore quantum materials. My group largely straddles the interface between development of new measurement techniques, measurement apparatus, and their use to extract meaningful information about quantum materials. And in this series of lectures, what I'd like to do is focus partly on the science that we're able to extract from in these materials that I'll describe, or phenomena that I'll describe. But at the same time, I'd like to convey a little bit the mindset that somebody like me, an experimentalist, has in thinking about new experiments or new ways of probing quantum materials. So before I get going, I'm curious to know how many of you in the audience are experimentalists? Okay, very few. This is actually good because my talk is largely about experiments, and so hopefully this will be instructive for the theorists. So I'd like to start from kind of a very broad picture. You know, our understanding of nature began a long time ago when we were only able to use our senses to explore nature. So we could, for example, study diffraction of light by looking at the rainbow. But today our understanding of nature spans a far greater reach. We know that our universe began 13 billion years ago. And we know down to the microscale that we have something called the Standard Model that describes things on the very microscopic level. And we even know what we don't know. We know that there's dark energy and dark matter, things that we know very, very little about. So the question is really, how do we know so much? And one of the things that I realized when I started as an experimentalist many years ago is that many of the measurement apparatus that we experimentalists use do not report the quantity that they measure. So the question is really, what do instruments measure? And this will be part of the focus of this series of talks, is to kind of make sure that there is an understanding of how is it that we are able to report quantities that we do not measure. So to get started here, I'd like to start with an example that we're all familiar with, and that is GPS. This is a measurement apparatus. We all know how to use it, and it reports our position with very high precision, down to maybe even centimeters, if it's not jammed. So the question is, what is the quantity that it measures? It doesn't measure position. Sure you know the answer? Yeah?
Triangulation from a satellite.
Well, it uses triangulation, that's true, but what does it measure?
The time,
Sorry?
The time that the light takes from the satellite.
Right, it measures time. So what we have is basically a set of satellites orbiting the Earth. They're sending a signal that has a well-defined timestamp of when that signal left the satellite. And what our little instrument here is doing is measuring when that signal arrived. But the connection between time and position is tremendously complex. It actually uses general relativity in order to be able to report position based on our ability to measure time. And this is really the essence of measurement apparatus. Measurement apparatus measures some quantities, but they use a really cool piece of physics, something that we understand fairly well, in order to report a quantity that we're interested in. And this repeats itself over and over again. I want to already motivate you to think about phenomena that you understand and to ask yourselves, well, using that phenomena, what quantities can I report that I was unable to report or explore before? And it's needless to say that the development of new measurement capabilities often lead to discoveries that we're really interested in. Now, once we're able to report position, we could basically say, well, we know how to measure position. And now we could use another piece of physics in order to report yet other interesting properties. And in fact, one quantity that we're able to measure can use many different chapters of physics in order to report many different quantities. And you'll see examples of that in the lecture series that I'll talk about today. All right. So in my group, we're basically developing a variety of measurement techniques. I'm not going to talk about many of them, but I just wanted to highlight what these are in case there's any interest. I'm happy to discuss this outside the lecture series. We're using superconducting circuits or cavity QED techniques to basically learn about superconducting properties of superconducting materials. I'll talk a little bit about the use of neutral excitation to learn about spin properties of quantum materials. And we've been using various local probes, one which uses a quantum dot, or if you will, basically a charge qubit, to measure interesting properties such as Chern numbers and topological properties of quantum materials. And much of what I'll talk in particular in the first two lectures is the use of a spin qubit, an NV center, to probe quantum materials. Now, before kind of jumping in deeply into what the technique is and how is it that we're able to extract information about the materials that we're interested in, I'd like to motivate a little bit why is it that we need new measurement probes to study quantum materials. After all, our tool set is already extremely, extremely developed. So why do we need more techniques? So I'll give just a handful of examples that I came up with, but there are many, many more. So if one thinks about ground state properties of materials, already there we are faced with some significant challenges. And here are just two examples. One is a quantum spin Hall effect. So here you see there is a quantum well, and there is a band gap in the bulk of the material. But because it's topological, it's a quantum spin Hall insulator, the boundaries actually consist of propagating edge modes that carry charge and spin. Interesting thing, because of the spin orbit and time reversal symmetry, it turns out that one charge state carries one type of spins in one direction, and the other one propagating in the opposite direction carries the opposite spins. So what is apparent here is that there is no net charge current at the boundaries because we have equally propagating edge modes on the two sides, in each side of the crystal. But what is not so trivial to see is that there's actually a net spin current, right? Because you're carrying one type of spin in one direction and the opposite type of spin in the opposite direction. So there's a net flow of angular momentum along the boundaries of this crystal. And this happens in steady state. So this is a steady state property. The ground state of this material carries angular momentum. I'm not familiar with any experimental technique that is able to detect the spin current today. So this could be something that obviously follows from the presence of this insulator. There are many other indicators that tell us that this phase exists. But nonetheless, this is basically a prediction that we don't even know how to test. Another example here is a sheet of graphene subject to a very strong magnetic field. And it turns out, I might have some time to talk about that in the third lecture, that these spins organize themselves in an antiferromagnetic arrangement where the spins are largely in the plane, perpendicular to the external magnetic field, and they're canted a little bit because of the magnetic field. And so the question is, can we detect this underlying order? Now, we do have techniques that probe magnetic order. For example, neutron scattering is a method to do that. But the problem here is that our material volume is one monolayer, spanning 1 by 1 micron. So the volume of spins is tiny. And the spin density, the magnetization density in this material is perhaps 1,000,000 times smaller than what it is in a real antiferromagnet, because the density of electrons here is very, very small. So conventional techniques are actually unable to look at this material and tell us this is the underlying order. So we're challenged to find ways of actually knowing that there is antiferromagnetic order in this system. So the challenge in these systems is not only quantities that we don't know how to measure, but also systems in which the volume or the existing techniques are incapable of providing information. Now, going beyond the ground state properties, one of the cool things about quantum materials is that they possess very interesting elementary excitations that go above and beyond the ground state properties. And often these excitations do not resemble at all the underlying constituents that make them up. And here are just a few examples. Skyrmions, I'm sure you've all heard of them in magnetic materials. In quantum Hall systems, these are actually real particles that are free to move around. They carry a charge E, but a spin that's much larger than spin of 1/2. And they're basically the elementary particles that live in the vicinity of filling factor 1 of quantum Hall systems. We all know that charged particles move in straight lines in the absence of a magnetic field, and they move in circles in the presence of a magnetic field. Well, in some quantum materials, again, 2D electron systems, in fact, you have particles that move in straight lines only in the presence of a very strong magnetic field. Only then they move in straight lines. And when you deviate from that very strong magnetic field, they start moving in circles. And these are called composite fermions. We have charge fractionalization. You've heard a lot about that. We have particles that have non-abelian statistics. In fact, these do not necessarily carry any charge. And they also don't necessarily carry spin, but they have some interesting statistics, which is non-abelian. And of course, you've heard, and you'll hear much more about spin excitations. These are neutral excitations that do not carry any charge, but carry quantized spin of 1/2. So visualizing these particles is also something that we're really interested in. Are these just the figments of some theorist's imagination, or do these particles really have existence inside the materials? And lastly, if we already have elementary excitations that are long-lived, can we study their transport? So we, of course, know how to study transport of charged particles because charge is conserved. But there's also some interesting predictions about the propagation and transport of spin excitations, work by Yaroslav here on superfluid currents of spin excitations. There's a lot of analogies between magnetic systems and superfluidity that I'll talk about perhaps in the second lecture. But the idea is, can we basically probe transport of these materials? But for that, we need to develop sensors that can measure the current of these excitations and effective potentials associated with these particles, which drive gradients of this potential, drive the currents, in order to study conductivity of whatever elementary particles we're interested in. So overall, we need to find our secret menu. We really are looking for new ways to probe matter, and this is largely the theme of my research group and what has been guided us for many, many years now.
Excuse me, can I ask you a question?
Of course.
So these magnons, how much do they propagate? Like, I assume that they dissipate as they propagate, or are they?
The superfluidity,
Oh,
or generally the magnons.
I guess both.
So unlike charge, spin is not a conserved quantity because you can have some spin momentum. So number one, charge can live in vacuum. Spin excitations must live inside a crystal. And inside the crystal, things are more complex. So you can have spin relaxation, predominantly from spin-orbit coupling. And so this is not a kind of a mathematically conserved quantity, but if it's kind of more or less conserved, you can talk already about chemical potentials and gradients of chemical potentials. And you can see the difference between diffusive and superfluid propagation of spin fluids. They have very different characteristics in material with weak dissipation. And Yaroslav can tell you much more about that. Yes, and please do ask questions because it will definitely help me set the pace. All right, so kind of the key probe that I'll talk about mostly in the first and second lectures is a scanning NV magnetometer. So I'd like to introduce it very kind of high level. I don't think the goal here is to teach you exactly all the physics that goes on in this, but just give you a flavor of what this sensor is about. It uses defects in diamond where We have a substitutional atom, a nitrogen, and a vacancy. These two atoms form an axis in space, and that is the axis along which we can measure magnetic fields. Diamond has a very, very large band gap, and the defect that lives inside this band gap exists well far away from the valence and conduction band, which means that we don't really need to worry about free particles in the diamond. Key property of this material is when you shine light on it, it emits red light. And as I mentioned, it has a very simple spectrum, which already Anna introduced, that lives well within the gap and is basically the ground state manifold consists of 3 states characterized by triplet. The ground state is magnetic field insensitive, and the 2 excited states, they evolve in magnetic field in a way that we understand very well. Basically with the G factor of a free electron, and each pair of these states we can think of just as a 2-level system that we're going to use. Another key feature of this system is that we can initialize it optically. So this means that even if this defect is at room temperature and the level spacing of this defect is much, much smaller than KT, if you just were to find an NV center randomly sitting around, you'll find that it is, the electron is sitting in one of these 3 states with equal probability because the temperature is so much larger than the level spacing. However, once you shine light, it turns out that there is a mechanism by which this system falls into the ground state. So effectively, we're cooling it down. And you can ask, well, what is this cooling process? How is it that we're able to extract entropy from the system? And this is a nice topic for coffee at some point if you're interested in. We can also determine whether this system is experimentally in its ground state or one of the excited states by the intensity of the light that it emits. It turns out that in the ground state, it emits more photons than it does in the excited state. And so just by looking at the fluorescence of this defect, we can say we're in the ground state or we are in the excited state. So how do we use this to measure magnetic field? Well, the simplest way is to shine microwaves. And what these microwaves are trying to do is excite the state from the ground state to one of its excited states. Now, unless the frequency of this microwave matches the position in which the magnetic field that we're at, we're not going to have any transitions. And this means that the fluorescence, the intensity of light that we'll measure, is going to be high. And once we find the right frequency that matches our magnetic field, satisfying this equation, then we will be kind of driven between these 2 states and we'll get a slightly dimmer response. Because now we're partly occupying the excited states and the ground state. And this immediately allows us to report magnetic field even though what we're measuring is fluorescence. So this is the link. We're basically measuring fluorescence and are reporting magnetic field. A nice thing about this sensor is that it's very insensitive to temperature, so we could work at a variety of temperatures. The scale, the length scale over which we're probing the magnetic field is really the size of this defect. So it's a very, very microscopic sensor. And we're going to make use of that spatial resolution as well.
Sorry.
Yeah, please.
Question. I didn't fully understand. What is the light driving here? So, because you said the valence band and also the conduction band is not touched.
Right, it's not touched. So actually, I did not show the full spectrum, but this ground state manifold sits somewhere in the gap. There is an excited state manifold for this defect, which also sits in the gap. And what this light does is make transitions from the ground state to the excited state back to the ground state. There are phonons involved, etc. I didn't want to go into all the details, and there are non-radiative processes that are also involved. But yes, there is another set of states living inside the gap that are. That's what the light is driving, correct. All right, so this is the simplest way of how to report magnetic field is by scanning the microwave frequency. There are in fact more clever ways of doing it, and that is by using real quantum control of this sensor. So this is a 2-level system. I could describe it when I choose 2 of the states out of the 3. I could describe it on the block sphere where the North Pole, let's say, is the ground state, and the South Pole is one of these excited states. And what is really needed in order to use this sensor as a quantum sensor is our ability to initialize, to control its state, and to detect whether we're in the ground state or the excited state, ideally in a single-shot manner. Doesn't have to be single-shot, but that's helpful. So the way we're going to measure magnetic field, so imagine we're interested in knowing what is the magnetic field that this qubit is subject to. So what we'll do is we'll initialize in the North Pole using light. We'll then use our microwave drive to prepare a superposition. So we'll do a pi/2 rotation to prepare a superposition of the ground state and one of the excited states. And then we'll let it evolve over time. That evolution will generate a phase. And of course, the bigger the phase, the more sensitivity we'll have. But the phase is directly proportional to the quantity we're interested in reporting, omega. And of course, the maximum time we can allow this system to evolve is its coherence time. It's basically its memory time. Once we exceeded that time, that information is lost. Now, in designing any experimental apparatus, you always want to know sensitivity versus noise, right? Basically signal to noise. We're competing with some unknowns. So since this is a quantum sensor, in fact, when we project it, when we try to measure, are we in the ground state or excited state, we're always going to get one answer, either the excited state or the ground state. We're never going to be able to measure the phase in one measurement. So in fact, our uncertainty in phase is pi. It's the maximum uncertainty in every single measurement. But using the standard limit, we can reduce that uncertainty by doing repeated measurements. So we'll initialize again. We'll prepare the same superposition, let it evolve in the same magnetic field. And over time, we're going to reduce that uncertainty by square root of the number of measurements. And so it turns out, we don't need to go through this math, but that our sensitivity in magnetic field scales as 1 over square root n and also improves with the coherence time of the sensor. So that would be a very effective way of measuring magnetic fields, very sensitive way. For example, we can have sensitivities in the nanotesla range, and just to give you a scale, the magnetic field that 1 proton is generating at a distance of a few nanometers is 1 nanotesla. So it's pretty sensitive. Once we have this kind of control developed, we can introduce more complex control over the block sphere that would allow us to extract magnetic field information also in the frequency domain. So not only static magnetic fields, which is what I described up to now, but also dynamic. So here, for example, we have a scheme by which the superposition that we're preparing evolves for some time, but after that time, we have a pi pulse that flips the sign of this phase, and then our evolution continues, and only signals that are changing in sync with our pulse sequence will be accumulated, and every other signal will be basically averaged to 0. And so these techniques, these control techniques, really allow us to extract detailed information about the spectral content of the magnetic field. So not only the DC magnetic field, but we can explore what is the amplitude of noise or coherent magnetic field signals as a function of omega in a range of frequencies going all the way from DC to several gigahertz. A little bit on the experimental side. So since we do have spatial resolution with this sensor, what we do is we fabricate these diamond cantilevers. There are many different versions of that today. This is kind of the operating version. We don't need to thin the diamond so much as to make it this kind of very beautiful and elegant slab of a few microns. This is actually a 50-micron slab, 1 pillar of diamond sitting at the end. You can see it here. And at the end here, we have just one of these NV centers, one defect sitting at the apex of this column, few nanometers from the surface And so this pillar here serves many different purposes. One, it serves as a atomic force microscope, so we can scan around to know our topography, where it is that we are over the sample. And it serves also to collimate the light through this pillar so that we're optimally collecting the fluorescence from this defect. As I repeatedly mentioned, really what we're measuring is fluorescence, so the more photons we have, the better signal to noise that we have. Yeah.
So if you have a single NV center on a tip like that, you lose the directionality information of the magnetic field. Is that correct?
Nope. Why would you say that? There is still, that single NV center has an axis.
Yes, exactly, but it can in principle really only measure along this axis.
Correct. So you're measuring only the magnetic field projected along that axis. But you'll see later on, I think tomorrow, that measuring one component of magnetic field is enough in order to determine all components of magnetic field. So in fact, it is a vector magnetometer under the right conditions, but, and I'll talk about the conditions tomorrow. Yeah?
Just a small question. How do you make sure that on this tip, which is like up to
100 nanometers, yeah.
100 nanometers, you have a single NV and not two NVs and not five NVs inside of the, you wouldn't be able to distinguish between them.
Right, so, I'd like to separate two things. One is how do we know that we have one, and two is how do we prepare the system so that we have one. So the preparation is done stochastically. So before we etch away these pillars, so everything here is one chunk of diamond to start with. This pillar is not attached to the end, it's basically etched, okay? So what we do on the bottom surface before we etch these pillars is we do the implantation. So we implant the nitrogens and we anneal, so we get kind of an ensemble of NV centers sitting, let's say, a few nanometers below the surface. The density of implantation is done such that on average, we have one NV center per pillar diameter. So it's an average thing. And now once we etch the pillars, so we have this typical area, so on average, among the different probes that we prepare, we're going to have one NV. Sometimes we're going to have none, sometimes we're going to have two, maybe three. The way we determine whether we have one is by photon correlations. There is a very specific method that can tell us whether we have one and no more than one NV in that system. And so we make hundreds of these probes at once. We'll then characterize them automatically. We'll let the program run overnight. And we'll choose those probes that have one NV. And simultaneously, we'll also characterize the orientation. So along what axis are we measuring? And choose those according to our application. All right. So in the scheme of things, oh yeah.
Can you do this process to put two pillars some distance away from each other, for instance?
You can definitely, so in fact, most of our probes have multiple pillars. I haven't shown it. There are many reasons why we'll make our probes to have actually multiple probes, and we'll basically tilt it around so that we choose which one we're measuring. Currently, the distance between probes is on the order of a micron, but we can make them closer. But if you want more than one sensor, you could also have deliberately designed to have two NVs within one pillar, and then you can do some interesting correlation measurements, and there will be a talk this week about correlation measurements from the group of Natalie Delone. All right, so in the scheme of what do instruments measure, I want to emphasize again that what we measure is fluorescence, and what we know how to report is magnetic field. We're using our knowledge about the defect properties and how this defect band structure behaves. I didn't emphasize this, but in fact, I know how to report also electric fields and temperature with this defect, but it's not going to serve the topics that I'm talking about today. That's why I did not mention it. And, yeah.
If users have only single defect in the NV center, so how can you make sure, because the signal is very weak, there's only one NV center, so how can
Right. So what helps us in detecting a single NV is this pillar structure. So we do want to collect as many photons as we can. And in fact, from a single NV, we can collect enough photons that allow us to average out the signal and determine what the magnetic field is with the resolution that I mentioned. So I don't know, maybe something that will scare some of the theorists, but sensitivity is always measured in some physical units like magnetic field, Tesla. But it's not enough to specify what the magnetic field sensitivity is, because you need to specify what is the time over which you average that signal. So normally, measurement quantities are reported in, let's say, Tesla per root hertz. Because if you increase your measurement time, I could just average, if I have a static magnetic field, I can just measure it longer and longer and longer, and my noise, I'll be able to average it more and more, whereas the signal stays constant. And the way I'll improve my sensitivity only improves with square root time. So it's not a very good strategy, but it's not a bad one. As I showed before, what really governs the sensitivity is the coherence time. If I'm able to improve coherence time, I will win a lot in my sensitivity. So making sure that these NVs have long coherence is also something that we strive for. Okay, so now that we've covered how NV centers work, I'll basically assume that what we know how to report is magnetic fields. And what I'll do throughout the talk is basically, describe both the physics that we're using to report yet additional quantities about quantum material and the physics associated with with these quantities. Okay, so just kind of a brief overview of what the lectures will cover. So this lecture, I don't know if I'll get to the end of it, but what I was planning on covering is looking at electronic properties of quantum material, and specifically to be able to report on the presence of electron hydrodynamics and kind of current flow in Josephson junctions below the critical current, which is actually very hard to infer what happens in a Josephson junction in the superconducting regime where its resistance is 0. And then if there's time, I'll talk about superfluid density, basically using magnetic fields to measure property of a superconductor. This will use BCS theory, and here we'll just use the Fourier representation of the Biot-Savart law to report current distributions in relation to magnetic fields. Second lecture, my hope is to cover spin properties. So whereas the topics today are going to cover electrical properties, tomorrow hopefully will be spin properties. So we'll look at the imaging of magnetization. We'll see that in order to connect magnetic field to magnetization, Maxwell's equations are actually not enough. One needs some input about the physical properties that you're trying to image in order to be able to report magnetization. And I'll also talk about spin chemical potential, some work we've done a few years back with Yaroslav, and about magnon hydrodynamics. So I'll explain what that is. These two properties will use the fluctuation dissipation theorem to report noise measured by the NV center, magnetic field noise, and these properties of spin chemical potential and magnon hydrodynamics. And then the third lecture is going to be, and now for something completely different, a la Monty Python. So our goal would be to basically use magnons as probes of quantum matter. So whereas up to now we've used our NV centers as a probe of quantum matter, now we're going to be using magnons. So I'll talk about the use of spin wave theory in order to extract interesting structure factors of quantum materials. I'll talk about the use of magnons in other systems, not magnets. In fact, there are magnets, but they're called quantum Hall ferromagnets, and the use of magnons to explore spin transport through various quantum Hall phases. And once establishing this technique of using magnons to probe spin transport, we're going to use that to develop yet another scanning probe microscope that looks to image in real space how magnons are propagating in these quantum Hall systems. And if there's time, I'll talk a little bit about the interface of magnons and superconductivity yet with another technique. I don't know if we'll have time. So before moving on and kind of starting onto the topic of electrical properties, I want to stop here and ask if there are any questions about this kind of very long-winded introduction. Okay.
Maybe I do have a question that always bothers me, so let me ask you as an experimentalist. We always need, as you emphasized, from the very beginning to repeat measurement, because for instance, in one shot, we are going to get a random variable, so there is a need to average. How do you really ensure that each trial, each run is identical to one another, given that we have the degrees of freedom we really want to monitor, but there is also an environment around. And I mean, in principle, we should bring that back as well to exactly its same initial state. But how do you know that?
Right. So you know, one of the cool thing about science is you never really know anything.
Right.
The only thing we do know is when things are inconsistent, right? So we know how to disprove things. We never know how to prove anything. And I want to comment before kind of diving into your question also the point that when I say we use physics that we understand, we never do understand physics all the way, right? We don't know for sure that there is something kind of hiding in the dark that we're not kind of accounting for. And it's really a complex thing because we're interested in reporting quantities that we don't know much about using something that we think we know something about, but we might not know it enough, or we might be using it in a range of parameters or conditions that are not appropriate. So there are many, I think this question is very, very appropriate. The key thing is repeatability.
Yeah.
And what you want to do, the idea of averaging is that things that are not interesting to you will eventually average out. This is an assumption, and it's not always correct. It might be that you need a very long time in order for things to average out. But in that sense, what will happen is that you'll basically figure out that what you thought is the physics that connects your measurement quantity and the reported quantity is you don't understand it well enough. So I think it's really kind of a cycle. If you are at a point where you see inconsistency, you go back and you look either at this physics or whatever you think your understanding here is, and you try to converge. But I don't think there is kind of except for repeated experiments and looking for consistency, there isn't really much more methodology that I could.
Because there are people, including myself, but not only, there is already some papers in the literature where, because we have the sensor, we actuate the sensor, meaning we control it. But if it is coupled with a quantum bath, the quantum bath can, in itself be modified and respond. And so the statistics of the outcomes that one might measure might be sensitive to that. So there is one paper, I don't remember the author, that talks about how a qubit can steer an environment in a certain way. And of course, this also affects the premise, like you do this independent trial, they are no longer identical independently ID as one assumes for the central limit theorem.
Correct. Right. So in fact, Ash has many interesting, works on exactly the back action of how the environment affects your sensor. And this is the physics you must account for if you want to eventually find consistency. And the hope is that if you're not accounting for this kind of physics, you'll basically get inconsistency between what your expectations are and what your observations are. This is the only insight we have as to what's going on, is inconsistencies. If everything is consistent, we're done.
I was wondering something. So the fact that you have always to average over a certain time kind of limits you to look at systems that are somehow time translational invariant or always steady states, right? And what is the time over which, how much out of equilibrium physics can you see in the quantum material that you are looking at?
So, okay, I think there are many different meanings. You know, you can have a dynamical phenomena. Suppose you have magnons that are, you're generating and they're propagating. You could generate them in steady state and then they will propagate in steady state even though this is out of equilibrium. Nonetheless, the system is continuously behaving in a similar manner and you can probe it and I'll show that. If the system has some random stochastic something, then you would need to necessarily be able to know something meaningful about your system within a short time scale, and you'd need probes that have enough signal to noise to tell you something meaningful over that time period. But you're right, it's difficult. Yeah?
Just a very quick question. So when looking at electrical properties, as you mentioned, there's also electric field that's coupling directly to NVs, but like for most purposes that will be neglected.
So the way the NVs couple to electric field is very different from the way it couples to magnetic field. So if you want to, and you can separate the two. So if you're suspicious that you have some, now the sensitivity of NV centers to electric field is far, far lower. So typically what would happen is if you're trying to sense a very, very weak magnetic signal, you might worry that part of that signal is a result of some very large electric field. But again, the response of the system is very different, and you can do a measurement that will distinguish between magnetic field, electric field, and temperature.
So it's something that you always kind of worry about a little bit? Or
I wouldn't say always, but if the signal is very, very weak, I mean, we have experiments I'm not going to talk about that measure electric fields using NV centers and image them in space, etc. There are instances where you're interested in both. Such as hydrodynamic Hall effect, where you have both a magnetic signal and some interesting electrical signals that could arise. In that case, you'd want to do both simultaneously, but it's basically you'd run these experiments parallel to one another. You'd run one sequence that's mostly sensitive to magnetic field, insensitive to electric field, and vice versa. Okay. All right, so 5 minutes to go doesn't leave us a lot of time, but let's start with the first problem that I wanted to discuss, and that is electron hydrodynamics. So in most metals, dirty metals, what you'll have is you'll have electrons, and these electrons will lose their momentum on average due to impurities or phonons or crystal boundaries. And so, and this is what we know about Drude physics. This is kind of the classical theory of conductivity. You can be, however, in a limit where the system is extremely clean, in which case the system doesn't have any mechanism of losing its momentum. But if you ask each individual electron, it is not going to conserve its own momentum or energy because it interacts with other electrons. So what happens is that each electron has momentum relaxation and energy relaxation, but the collection of electrons conserve energy and momentum. And this is the limit. This is what's known as hydrodynamic limit. We're familiar of this kind of behavior in gases and fluids. Airplanes fly because of the hydrodynamic behavior of air, etc. Now you could ask, well, in what electrical systems would we encounter hydrodynamic behavior? Well, it turns out that what you really want is very long basically, you want strong electron-electron interactions in relation to the momentum relaxation rate, and you can find this actually in low-dimensional systems. So I'm going to be very brief. What we know about Drude conductivity is that because of the average momentum relaxation, there is a relation between the electric field that the electrons feel and their saturation velocity. And that's what defines the mobility in the system. So the system is characterized by mobility, which is basically the ratio between the saturation velocity and the electric field that is applied. Because of the interaction between electrons, what happens is that there is an additional term that basically exerts forces on the electrons. If I have electrons in one side of the sample that are moving fast and ones that are moving slow, there will be friction between these because the fast one will want to kind of pull along the slow ones, and you'll get redistribution of velocities in the system, and that is given by this viscosity term here and is proportional to the second derivative of the velocity vector. So one of the interesting things is, as we know from fluids and gases is that hydrodynamics has a profound consequence on how flow of material, matter, atoms, liquids appears, let's say, in a pipe. And the question would then ask is, well, is there something similar for electrons? Suppose I take a copper wire and I ask, how do electrons flow in this copper wire? Am I going to see this kind of Poisson flow, which basically requires the velocity to go to zero at the boundaries because of the loss of momentum in the boundaries, and has this universal parabolic shape due to the viscosity nature of the fluid? This is what happens in water in a pipe or air moving inside a pipe, etc. This is hydrodynamic behavior. So it turns out that the answer is yes. And the way we can probe it is we can prepare a channel. So this is, the red here is the channel in graphene. So there is a monolayer of graphene here that we're sending current across. You can see that the current is sent in from this contact through this narrow channel and coming out the top side. And we're using Maxwell's equations, basically a very simple relation, the Fourier transform of the Biot-Savart law, to connect the magnetic field that we can measure in space along directions x and y and the current densities. I want to emphasize that this is in momentum space. So as to Suzanne's question, if I were to only measure at one point and I would want to say what is the magnetic field along x and along y, I wouldn't be able to do it because I'd only know the projection. But if I know how to measure the magnetic field along one axis in all space, and I can take its Fourier transform, then I could infer what the magnetic field in all components are, and then I could immediately also infer uniquely what the current densities are in the plane. There is this factor here, which is a problem. It basically, d here is the distance between the NV center, our sensor, and the sample. And you see that in order to get the current density, I need to divide the magnetic field that I measure by this factor, which is exponentially large. And so this is, it's exponentially small. So when I divide by it, I increase my noise. This is a general property of deconvolution that, as an experimentalist, you have to struggle with. But nonetheless, if there is enough signal to noise, then you can do it. So what you can see here is basically the current profile. We can integrate this current to see what the total current is, and it agrees well with what we're sending through the sample. And we can take a line scan, and you can see that in graphene, the current density profile really follows very nicely this Poisson flow. So this is quite remarkable, right? This system of interacting electrons will have a net velocity, average velocity near the boundaries that goes to zero. This is not a must. It could be slipping boundary conditions, etc., but that's the experimental observation. And when you look at materials that have very strong disorder, like palladium, you see that the current flow profile is flat, which is what you would expect for the Drude type of resistivity. Sorry? There are many, so, as much as I'd like to think that this graphene is perfectly clean, it's not, and there's kind of location, there is some disorder, so the profile is not going to be perfect, but nonetheless, so, if you'd measure a different position, you'd get a slightly different curve here. But yes, if you would average many slices, on average, you're going to get a very nice Poisson flow. Yeah?
Why is the noise larger?
Good question. I don't know. I need to go back and look at that.
Can you remind us, theoretician, limiting factors of bringing D very close to zero? So up to which distance you are happy of letting your MVD? You're complaining about exponential factor, right? So that
right.
Plain-minded theoreticians, reduce D. Of course you can't. Why? Can you remind us?
Well, okay. So the ultimate limiting factor is how deep this defect sits from the surface of the diamond. So the best thing you can do is you bring your tip all the way and touch the sample. Under these conditions, you're going to be your depth, how deep that defect is relative to the surface. And you can ask, well, how close can I bring that? Really tour de force work by Nathalie de Leon, who's kind of really worked to maintain coherence. The problem is that when you make that defect closer and closer to the surface, it will suffer more and more decoherence from dangling bonds on the surface. But you can get that to be 2-3 nanometers. Diamond is a very hard material when you actually bring it very close to the sample, and if you touch the sample, it's going to cut it. So we're actually extra care to make sure that the diamond is touching or not touching the sample. So we would typically work a few tens of nanometers above the surface, even though we could in principle be closer. All right, maybe I'll try to just briefly talk about Josephson junctions, and we'll pause whenever you tell me to stop, and then we'll continue with the second lecture. It's fine. So just a brief introduction to Josephson junctions. These are ubiquitous at the moment. They're really one of the main quantum elements that are being used in quantum technologies, superconducting qubits. But they're in fact also useful as sensors. Here you see a photodetector, and here you can see a terahertz wave source. So there are many, many uses for superconducting Josephson devices. They're also being used for topological quantum computing. It's basically one of the elementary building blocks of using a Josephson junction with some magnetic field that break time reversal symmetry. It allows you to generate non-abelian excitations at the boundaries of these Josephson junctions. And it produces both triplet superconductivity, non-abelian excitations. So a lot of very fun and interesting physics can emerge from Josephson junctions. More recently, there have been a lot of discussion about the Josephson diode effect. So as you know, diodes have different resistance when you send current in one direction versus the other. The Josephson diode effect corresponds to a situation where the system has zero resistance when the current is flowing in one direction and has a finite resistance when it flows in the opposite direction. The question is, what are the underlying mechanisms that are responsible for that? So this is all physics that is happening within a Josephson junction. Can we say something more about these systems? So briefly, the Josephson effect is a result of the fact that when you try to connect two superconductors with a non-superconducting segment, you can propagate superconductivity because of the continuity of the order parameter into that normal or insulating region. And while the phase in each one of these superconductors itself is not well defined, the phase difference is well defined. And typically what characterizes the local properties of a Josephson junction is what's called a current phase relation. Namely, I can impose a current on this junction. This will necessitate a phase difference given by this relation. Alternatively, I can force a phase difference and will then get a current. So one could look at this both ways. One of the key signatures of a Josephson junction is the Fraunhofer pattern. So this is what you'd measure in transport. What you see is that as a function of flux, the critical current in the junction will oscillate as you're threading flux through the system. So since the chair is up, I'll pause here. We'll pick it up tomorrow and take questions. So last time I started by giving some broad introduction to NV center magnetometry and emphasized the need to use physics, various known physics, in order to connect the quantities that we're interested in reporting and the quantities that we know how to measure. And I'll continue in this vein today. I'll talk about imaging of currents in a Josephson junction in a regime where, this is not working, in a regime where the junction's resistance is below, is zero, so you don't have really any transport signatures to report what is going on inside. I'll skip the measurement of superfluid density and I'll continue to spin or magnetic properties. I'll describe imaging of magnetization, where we can image skyrmions, and we'll see that Maxwell's equations are in fact not enough in order to be able to report magnetization. And then I'll talk about some fluctuations in magnets that allow us to report spin chemical potential and observation of magnon hydrodynamics. So I already gave some introduction to Josephson junctions last time, yesterday. But I want to emphasize that a lot of what we know about Josephson junctions comes from the fact that we can study what its critical current is. So we send a current, it exceeds the critical current, and then we can see what its behavior. I'll show today that we can, using our magnetometry techniques, we can learn about what's happening in the system below the critical current, namely when the system is not providing us much information, its resistance is simply zero. I also want to emphasize that superconducting qubits that use Josephson junctions are yet another way to actually probe what happens in the Josephson junction below the critical current, which is very different from the one that I'll be describing here. So the key ingredient of a Josephson junction is the current phase relation. As I mentioned, the phase in each one of these superconductors is not well defined. The phase difference is well defined, and you can send a current through the junction which will generate a phase difference, or alternatively, you can force a phase difference that will then generate a current. This is typically, in Josephson junctions, a local relation. So if I have a junction that is extended, I can think of each position here as having a Josephson junction with a specific current phase relation, but this is now position dependent. And the amplitude of the current in each position, which is basically related to the normal state resistance of the material that separates the two superconducting contacts, can vary in position. The phase difference between the two superconducting electrodes, delta phi, is global, but we can also have a position-dependent phase that has to do, for example, with an external flux that is applied to the system. But if I have time, I'll mention that this does not necessarily only need to represent an external flux. There could be other sources of this phase that come in. So in the simplest case, when we do subject the system to an external magnetic field, this flux, position-dependent flux, is just linear in position. It basically tells us what is the enclosed flux up to a point x, where we assume that this flux is zero at point x equals zero. And so if we want to know what the full current phase relation of the complete junction, we need to integrate this current phase relation over the entire junction, and that is shown here, and that's a very simple integral to carry out, especially in this simple case. And what you find is what we're all familiar with, the conventional Fraunhofer pattern. So you see that the current phase relation is still sinusoidal. Now this is the current phase relation of the whole junction. It's still sinusoidal. The maximum current that will flow in the junction is given by the current density times the length, in the case where the current density is uniform, is constant in position. And we have this envelope function, this sine phi over phi, which gives us this Fraunhofer pattern that we're all familiar with. When the flux is 1 phi naught, we see that this term here vanishes, and the critical current in the junction goes to zero. Note, we can read out what the critical current of the junction is by basically asking, well, what phase difference will maximize this relation? Once we exceed that current, so namely when delta phi is pi over 2, so this sign factor is unity, if we exceed that current, there is no solution to this equation. We can't find a phase difference that satisfies this equation, and the system will go normal. So this is what we normally study in transport, and this is indeed a measurement, a resistance measurement in this junction at 7 Kelvin, so relatively high temperature. I didn't say that the junction is comprised of niobium and gold separating two niobium contacts. So it's a very trivial junction. But now let's ask, well, what happens if the current through the junction is zero? So the system is completely superconducting. Is there anything interesting happening? Well, we can see from the total current phase relation that if we impose a total current to be zero, the phase difference must be zero. And we can now plug this into this current density. So delta phi is 0. And this means that the current density as a function of position actually depends on position, and its amplitude is given by the maximum current density that would flow in the junction. So despite the fact that there is no current, global current flowing through the junction, once the flux is not 0, we will get currents flowing through the junction, even though there is no net current flowing from one side to the other. We can look at the other limit, and that is we can approach the critical current, again, but below the critical current, so the system is still superconducting. In this case, delta phi, as I mentioned before, is pi over 2. I can plug that in. The pi over 2 converts the sine to a cosine, and now I get, again, a current, position-dependent current density that will be non-uniform when magnetic field is applied to the system. And the significance of magnetic field, I'll say something about that later on, is breaking of time reversal symmetry. So in effect, when you break time reversal symmetry, you will get currents flowing in the junction that are non-uniform. So we could easily observe this kind of behavior. So here is just to kind of belabor this point, this is what the current density would look like as a function of flux when we're approaching the critical current. So at 0 flux, the current density is uniform because flux is 0, so we have just a uniform current density. But as we increase the flux, you see that the maximum current density is not changing, but its shape is changing, and we're going to get counterflow and forward and backward flow of current in the junction as we're changing the magnetic flux. And note that even at this point here, or this point here, where the critical current in the junction is actually 0, namely, I can't even send any current through the junction without turning it normal, I nonetheless will get a very intricate current flow pattern. So here are some images of how that looks. I already emphasized the connection between measuring magnetic field, which is what is shown in the color plots here, and the arrows are the current density and direction as computed by inverting the magnetic field into current density using Biot-Savart's law. And I want to emphasize that there is a unique connection between the magnetic field and the current distribution. There is no ambiguity. One infers the other. You can see, for example, that when the flux is just below the first node, we have current flowing forward in the middle, and once you just exceed a little bit the current, the flux to be above the first node, immediately you see a reversal of the current distribution, and you see this kind of flip of shape that occurs. And there are a lot of things that deviate in this measurement from the simple description of the Josephson effect that I just gave you, but this is not a talk about Josephson phenomena, so I just want to emphasize that there are a lot of puzzles that emerge. In particular, this Fraunhofer pattern was one that was observed at 7 Kelvin. If you just cool the junction a little bit to 4 Kelvin, the first thing you note is that the critical currents increase by almost an order of magnitude. But you also note that the nodes are lifted. Now, node lifting might have many different reasons. Okay? The simple picture that I described to you, where the current density is uniform, will not give you any node lifting. One can prove that rigorously. If the system is actually symmetric, then you cannot have any node lifting. The fact is that you have node lifting, and the question is really what's going on underneath, inside this regime. And so here again, we could use our magnetic field imaging to look what happens. So you see that we have very strong signatures of something happening inside the junction below the critical current, something that we have no indication of simply by looking at resistance. These are first-order phase transitions that occur in the junction near the first node that have to do with the entry of a vortex into the system. The same thing happens near the second node. Over here, again, we have some phase transition that takes place, and again, has to do with the appearance of two vortices into the junction. Something interesting that happens here is that you could see that you can control this phase transition simply by current. So by going from, let's say at this point, from zero current to some finite current, you will undergo a phase transition where you will kick in or extract one flux through this long junction. And the reason for the appearance of this has to do actually with the kinetic inductance in the system, and that is yet another way of getting phase. I mentioned that the phase that appears in the current phase relation is not only related to flux. In this case, it's related to the phase associated with currents flowing in the junction. And when the superfluid density or the kinetic inductance in the system becomes very large, what happens is that the phases that the current that is flowing in the system is generating can be very large and will affect the solution in the system. One thing that's peculiar about this system is that it shows a diode effect. Now, I mentioned what the diode effect is. The diode effect is when you send current in one direction, the critical current could be different from the critical current flowing in the opposite direction. And obviously, if you have a diode effect, you must break inversion symmetry. So something breaks inversion symmetry in this device. It could be, we're not deliberately breaking it. The device is fabricated to be symmetric, but the fact is that you do see a difference between forward and negative critical current as outlined by the blue symbols here. So obviously something is breaking inversion. But what is interesting is that simply breaking inversion and time reversal symmetry is not enough to produce the diode effect. And it's really just 2 lines of analysis to see this. This is the integral I mentioned before, and I have here a general flux that could depend on an external magnetic field. It could be position dependent. J here can depend on position, which allows me to break inversion. So if J of plus X is different from J of minus X, I break inversion. The flux here, or the magnetic field here, breaks time reversal symmetry. But it's very easy to show that this integral is just the imaginary part of a phase factor. And this is just a complex number. And I could write this complex number as some amplitude and phase. And I need the imaginary part of this thing, which immediately tells me that the current in this junction is still a current phase relation, which is sinusoidal. And this amplitude here is the critical current. And you see that the plus current, the critical current for current going forward or backward must be equal. So something else must be happening in this junction. And again, it has to do with the kinetic inductance in the system that generates nonlinearities in the system that I'm not going to describe. I'm happy to discuss this with anybody who's interested later. But basically, this allowed us to figure out that there is yet another mechanism, even in a system that doesn't have any intrinsic kind of topology or breaking of time reversal symmetry. You can get a diode effect that has to do with the kinetic inductance. And this actually is very interesting, in particular in relation to experiments done on 2D superconductors like twisted graphene, etc., where the superfluid density is very small, and that lends itself to very strong effects of this nature of the kinetic inductance. All right, so in the spirit of how things are being measured, so we're imaging currents below the critical current using this Fourier representation of the Biot-Savart law, and I also emphasize this exponential factor that makes this conversion from field to current density somewhat problematic, especially if the spatial dependence of the currents that we're trying to image are oscillating faster than the distance d to our detector.
How weak are these signals with respect to the ones that you could get from, I don't know, some ferromagnet?
So the signals here are in the range of microtesla. So these are kind of convenient magnetic fields. In a magnet, you can get much stronger magnetic fields, but okay, it will depend on the context, and you'll see this in just a bit, because you can also get very small magnetic fields from a magnet. So we'll talk about this just next. Okay. So I'd like to transition now to talk about spin properties of magnetic system of materials, in particular magnetic materials, and I'll start with the imaging of magnetization. We've heard a great talk by Aurora yesterday about skyrmions and domain walls and the physics of DMI, the Dielozinski-Moria interaction. So I'm not going to talk about that, just to say that in certain materials that indeed break inversion, and this could either be bulk crystals or stacks of crystal where inversion is broken by basically having two different materials sitting one on top of the other, these type of materials can lend themselves to the formation of skyrmions, which are these textures of magnetization. I also mentioned that in certain systems like quantum Hall systems, these actually become particles that are mobile and have spins that are generally much larger than 1/2 and still carry a charge of 1 electron. These structures have a topological content, and the way you could see that is by mapping the local magnetization of the entire texture onto a sphere, where each point on the sphere represents an angle, a direction. So for example, this point here in the middle is basically going to be mapped onto the South Pole. All the spins on the outside of this texture are mapped to the North Pole, and in between, you could see that we have basically a representation of every angle on the sphere. So what's interesting about these structures is that indeed they cover the sphere and precisely an integer number of times. So either 0, 1, 2, it has to be an integer. One could show energetically that covering the sphere non-integer number of times is energetically unfavorable, and the system will tend to relax to an integer configuration, either having no wrapping, which means just a ferromagnet, or textures where it's wrapped 1, twice, etc. So the goal is to image these things, and in fact, we could see their signature quite easily. So this is just a fluorescence map. So remember, what our NV center is, what we're doing is we're measuring fluorescence. So we're shining some green light, we're getting some red light out. These are maps of the reflected red light as a function of position in a stack of some magnet on-site platinum that has strong spin-orbit interaction, and you can see very clearly the domains. The reason you're seeing contrast just in the optics here is because the magnetic field patterns generated by these domains could be fairly strong and could appear perpendicular to the direction of the NV axis. And when that happens, fluorescence diminishes. So this is the contrast, but it's a very non-quantitative way of describing what's going on. In particular, note that at low magnetic fields, we have just domain walls, but as we're applying some magnetic field to the system, we have some interesting candidates for skyrmions or some tiny bubbles, if you like, where the domain wall is now kind of fully enclosed on itself. So let's see what a magnetic field, a quantitative magnetic field image shows. So remember the NV spectrum, it has two transitions from the ground state to an ms equals -1 and to a ground state and ms equals +1. And because we have strong off-axis magnetic fields, we actually need to measure both. If our magnetic fields were relatively weak, then we would only be sensitive, as I explained initially, to the magnetic field projected along the NV axis. Here magnetic fields are fairly strong. We need to be able to account for both off-axis and on-axis magnetic fields, so we need to measure both transitions. So what is recorded here is just the microwave frequency that generates transition at any given point in space above this structure. And you see this is the frequency, and this is the spatial map, and this is for the lower transition, and this is for the upper transition. Now you can use our understanding, again, of the physics of NV centers. I'm not going to go through it, but basically the use of these two quantities allows us to extract the magnetic field parallel to the NV and magnetic field perpendicular to the NV. And note, the one perpendicular to the NV is very noisy. And the reason is that we're not linearly sensitive to that quantity. It comes in only quadratically, and so we're getting kind of a crappy visualization of the perpendicular field, but nonetheless, we can see that it's there. And the field is not that small. You can see the scale here in Gauss. It's not that small, but it's quite noisy because our technique is not really effective in extracting that quantity. So now our challenge is to use this magnetic field and convert it to magnetization. And this seems like a very easy problem because, hey, we know Maxwell's equations, there's magnetizations, there's magnetic field. We should be able to go back and forth from one to the other. Turns out that that's not so easy, and I want to kind of emphasize this. So first, let's see what our NV center is measuring above a magnet. So this might not surprise you, or to some it might be a surprising result, but if I have a film that's uniformly magnetized, just a nice magnet, it is actually not producing any magnetic field in the bulk. The reason is that if you think about each one of these dipoles as a small electrical current, and I span my entire space with tiny current loops, you see that all these currents in the bulk vanish. They cancel each other. So there is no net current, effective current flowing in the bulk. The only reason I will detect a magnetic field is if I'm close to the boundary. There, the currents don't cancel. But it's a very weak effect, and if I'm very far from the boundary and I'm close to the magnet, in fact, a magnet is not producing a magnetic field. So this makes it really hard for us. That means that structures in magnetization that have very long wavelengths will not produce magnetic fields that we can measure. Conversely, if I have a magnetization texture that oscillates really fast in space, faster than the distance to the NV, then the contribution of the magnetic fields that are generated are all going to cancel out, and I'm also not going to pick up a signal. So at the end, what I have is that if I want to describe my magnetization textures in terms of its wavelength or its wave number, you see that our sensitivity goes to 0 when the wavelength is 0. Sorry, when the wavelength is infinity, k goes to 0. It exponentially decays for very large oscillating magnetization, and it actually peaks precisely at a wavelength corresponding to the distance to the NV. So first of all, changing the distance to the NV is very efficient, very useful, because I could explore different momenta of magnetization textures. But nonetheless, this is kind of our spatial filter function that we need to live with. Note also that this filter function here increases linearly with k. And since this is Fourier space, anything that's linear in k suggests that in real space it's a gradient. So in effect, what we're sensitive to are gradients. Long wavelengths, we're sensitive to the gradients of magnetization, not the magnetization itself. So this is already a challenge. We want to report magnetization. So now we can kind of go and dive a little bit into the detail and say, well, okay, so what is the magnetic field generated by some structure? Well, I can take each dipole here, and it's generating some magnetic field at the position of our NV, and I need to integrate over all dipoles, and I get a convolution. Where this matrix here is the dipolar tensor, it basically connects a general orientation of a magnetic moment with the magnetic field it's generating at some arbitrary position in space. And each one of these magnetic field components, x, y, and z, I'm going to look at it at a particular height d and as a function of all space. So it's each one of the three components depends on x and y. Basically, it's a spatial dependent quantity, and I could look at its Fourier transform, which has a magnitude k and a phase phi. So it's done in polar coordinates. And this is the dipolar matrix in these polar coordinates. And you see that doing this calculation produces this filter function, this prefactor here, that goes away at k equals 0 and becomes exponentially small at large k. So this is what we expected. But there is something surprising in this dipolar matrix, and that you note that all the rows are linearly related to one another. So if this is, let's call this row 3, this one is proportional to it, and this one is also proportional to it. So what the significance of this is simply to say that if I measure one component of magnetic field, you see that I can immediately figure out what the other two components are, because they're just linearly related. And this is, again, not a surprise. I'm measuring magnetic field in a place in space where I have no currents. So this means that the curl of the magnetic field is 0, and basically I can define a magnetostatic scalar. So it's one function that has only an amplitude that depends on position, from which I can derive all three components of magnetic field. So this is not that surprising, and it's very useful. So let's use it.
Sorry, excuse me, can I ask you a question?
Of course, yeah.
Just to make a connection, if I think of atoms coupled with fibers, it's the same. Like you have this suppression of the coupling that is exponential, but then what people do to enhance the coupling is to change the dispersion relation of the photons. So they go to some slow light type of medium. So can you do something like that here? Or?
Yes, so in principle, I can imagine having some material that kind of separates my NV center from the material of interest, maybe a mu metal, something that would have kind of an interesting dispersion relation that would allow me to maybe kind of relax some of the difficulties. But in fact, this is a plus. This is a bonus for us. So I don't want to relax this. You'll see in a minute what I do want to relax, but this is really good, because now I only need to measure one component of magnetic field. I measure it along the NV axis, and I'll be able to.
That part
Yep.
I understand, but it's more about the coupling, whether it is efficient or not efficient.
Well, the coupling is, so for us, we can easily detect, I wouldn't say easily, but if we have our NV center sitting maybe a few tens of nanometers above a single spin, we can image its magnetic field in space. So it's pretty sensitive. And if we get closer, we can even image that of a nuclear spin. Okay, so this is the magnetic field map that I already showed you, parallel to the NV axis. But now, because I know the dipolar matrix, I can now extract from this all three components of magnetic field in space. And of course, I could compute also what is the magnetic field perpendicular to the NV. And remember, I was able to measure it, but it was noisy. But now, because I can basically extract the perpendicular component from the parallel component, it's no longer noisy. So I'm getting exactly the correct perpendicular component of magnetic field, but now linearly in magnetic field with a very good signal to noise. The not so nice property of this relation is that because all rows of the dipolar matrix are linearly related, it has no inverse. The challenge of getting magnetization for magnetic field is finding the inverse, is basically multiplying the measured magnetic field by the inverse of the dipolar matrix, but that does not exist. And what this basically says is that there are an infinite set of magnetization patterns that produce precisely the same magnetic field. Yeah?
Do you not have the same problem for current distributions if it's a three-dimensional current distribution?
You do. In 3 dimensions, you have the same problem. You cannot invert this problem. It does not have an inverse. In 2D, which is what I was describing, you do, and that's why it's so nice to use this for 2D problem. But yes, people are trying, for example, to use magnetic field imaging to image brain activity, etc. You have a complicated array of axions, etc., and extracting what the topology and architecture of that from the magnetic field is not an easy problem to solve. And here, we cannot just use Maxwell's relation to extract magnetization. So we need something else. And what we're going to use is the fact that these textures are topological. So this is the measurement of the magnetic field. And what we're going to be doing is we're going to kind of guess magnetization textures and compute the magnetic field that they generate. And as I emphasized, there are 1 million and more configurations that will produce precisely the same texture. But what we're going to be screening things is by how these textures map onto the block sphere. So for example, this texture, which corresponds to a block skyrmion, namely the spins actually rotate in a tangential direction as you move along the radial, and they only cover the sphere by half the amount. Whereas if you were to choose a texture that is a nail configuration, you see that it covers the full block sphere, which means that it is a physical solution. So we cannot find precisely the texture by this technique, but we can certainly find a class of textures all agreeing with this kind of nail solution that are very consistent with the data, and you can see the agreement between the field generated by this texture and the dots, which are the measured ones. So this basically helped us kind of figure out, and there's a puzzle there again. I don't want to talk about it because we didn't expect this particular solution, but nonetheless, we think we have an understanding. So in this case, the physics that is needed in order to connect measurement of magnetic field with magnetization is obviously the Maxwell's equations, magnetostatics, but also one needs to invoke another piece of physics that we know about the system in order to do this conversion. Yeah.
Is this ill-determined problem? Is that also if I measure multiple depths, for instance, it's still, I know all of the field for all distances throughout all?
Yeah, so if you know the field in one plane, you know it in all planes.
Okay.
So, no. All right. So now I want to move on and talk about fluctuations in magnets. So we know that the elementary excitations inside a magnet are magnons. These are kind of nearest neighbor interaction between spins. And I already mentioned in the introduction that if these magnons are long-lived, then one could define a chemical potential. And of course, what drives currents, spin currents in the system, are gradients in chemical potential. But so what we'd like to understand is how does this chemical potential depend on the density of magnons in the system? It turns out that there's been a lot of interest in the problem describing magnons in magnets. I mentioned this work by Yaroslav, recent work, but the field actually began maybe 50 or 60 years ago by Halpern and Hohenberg, where they write in the introduction that a hydrodynamic theory of spin waves is developed for certain magnetic systems in analogy with the derivation of two-fluid hydrodynamics for liquid helium. And I want to say that the meaning of hydrodynamics in this content is different from the one that I mentioned. It has to do with spontaneous breaking of symmetry. But the hydrodynamics is not so important. It's the superfluidity that is perhaps important. So what do we know about this system and about superfluidity in this system? So first, some property of these spin waves. So these spin waves are what are shown here. They're kind of just small correlations between nearest neighbor spins, and these can generate waves that propagate. In their quantum version, they will have a quantized angular momentum, a spin of 1/2. And if the system has some anisotropy to it, let's say either a crystalline anisotropy, or I can generate the anisotropy by applying a magnetic field onto the system, then what would happen is that tilting the spins away from this anisotropy costs energy. And if the anisotropy is magnetic field, we'll get a spin gap. We'll get a region here in energy where these kind of magnons cannot exist. And this spin gap increases according to what's known as the Kittel law. It's a square root law at low magnetic fields. Above this gap region, we do have the magnons. And typically in the experiments that I'm describing, temperature is much larger than this spin gap. So we actually have quite a large soup of magnons that live in the system, despite the fact that there is a spin gap in the system. This is a bosonic system, so we know that the relationship between chemical potential and density is, for a bosonic system, is such that the chemical potential could be negative in principle and then will increase. But at a point where the chemical potential reaches the first available state of the system, it will get pinned. And the reason it gets pinned is because we'll start having macroscopic occupation of the ground state. So we'd like to see if we can see this kind of chemical potential as we're increasing the number of magnons in the system. I'm not going to tell you how we're increasing the magnons in the system, but we know how to pump more and more magnons into the system. So the way we're going to probe what the chemical potential is, so the chemical potential obviously related to the number of magnons in the system, and the presence of magnons, this is just kind of a thermal cloud of magnons. Each one of these magnons is oscillating in time at the frequency given by the energy of the magnon, so it is generating a magnetic field, time-dependent magnetic field in time. And the collection of all these magnons are generating noise. If that noise actually is at a frequency which matches the transition frequency of our NV center, it will cause transitions. So a time-varying magnetic field that is resonant with one of these transitions will induce a transition. So just by measuring how fast does the NV center leave its initial state tells us about the magnitude of the noise at a particular frequency. So it's a very, very selective frequency spectrometer of noise. So the occupation of magnons depend, of course, on chemical potential, also depend on temperature. I'm not going to describe how we know what the temperature in the system is, but it is not changing as we're pumping magnons. Again, we're using the NV center to measure temperature, but why is it not changing? I'm not going to emphasize. And we're going to be pumping magnons more and more into the system. So the decay rate of our NV center now is going to be not only proportional to the occupation, but also to the density of states of magnons. And this might be a complicated function. But the important thing is that we're measuring at a very, very narrow frequency band of frequencies, because we're only sensitive to things that are happening precisely at this frequency with a very, very narrow bandwidth. So we only need to know the density of states at one particular energy. There are no integrals here. This is all happening at one energy. And so if we can do an experiment that has two different chemical potentials, we can just take the ratio of the rates, and that will cancel out the detailed property of the material itself, leaving only the Bose factor for us to worry about. And this is how we can extract chemical potential based on two measurements, one in equilibrium and one with a drive. The only other quantity that we need to know is the actual energy separation of the NV center, which we know very precisely by other means. So we have a completely parameter-free way of extracting chemical potential in this system. So this is work that we did with Yaroslav a couple of years ago, where we're extracting here the chemical potential in the system as a function of the number of magnons that we're pumping into the system. And remember, what we expect is that this chemical potential to increase and eventually saturate, and it needs to saturate precisely at the bottom of the spectrum or at the top of the spin gap. And this is exactly what you can see here. So different magnetic fields. You see that the chemical potential, so the magnetic field controls the spin gap in the system, which is this black line. And you see how the chemical potential, just extracted from these simple relaxation measurements, increases and then saturates precisely at the bottom of the spin gap, very much in accordance with what we expect for a Bose distribution. So this is was a very nice success on our part in being able to extract a quantity that, again, is very, very hard to extract, spin chemical potential inside a magnetic system. In the schemes of what do instruments measure, here we use the fluctuation dissipation theorem that relates the fluctuations in the magnet to the dissipation of the NV center in order to report chemical potential. The last topic that I'd like to talk about today has to do with magnon hydrodynamics. So I already mentioned that the system of magnons here has a gap. So I'd like to ask, are there any fluctuations in magnetic field that occur at frequencies that are below the gap? From this picture, it might seem like there shouldn't be, because I cannot have any magnons below the gap. Suppose there were fluctuations below the gap, how would we measure them is yet another question, because typically the transition frequency that I've used before to measure the fluctuations in the magnet, they are kind of sitting nicely well within the spectrum of magnons. I actually want to be able to be sensitive to very low frequency fluctuations in the kilohertz range rather than the gigahertz range. So how would we do that? And I already mentioned that in the introduction of NV centers. We use pulsed control of the NV center to choose a filter function, this time a frequency filter function, that selects a bandwidth of frequencies. And the way this is done is the simplest one of them is what's called an echo experiment. So you prepare your NV in some superposition state and you let it evolve in the presence of whatever is fluctuating in the environment. And then you induce a pi pulse and you let it evolve some more. And the cool thing about this thing is that you see that if the magnetic field is constant in time, then this technique will produce a precise 100% echo. So it's basically completely insensitive to magnetic fields that are time independent. So omega equals 0, you see this filter function goes to 0. We're filtering out anything that's not time dependent. Depending on the evolution time of the sequence, tau, this filter here is going to be peaked at a frequency given by 1 over tau. And so typically this system that has some noise will have some echo time that we can run. So this time is going to be somewhere in the range of, let's say, 10 microseconds or 100 microseconds, which means that we're mostly sensitive to fluctuations in magnetic field in a bandwidth of several kilohertz to 100 kilohertz. I already mentioned the spatial filter function of the NV sitting at a distance d. We're not sensitive to fluctuations in space that are long wavelength. We're also not sensitive to ones that are short wavelength. We're sensitive to ones that are more or less at a distance 1 over d. So these are the parameters in spectrum, in omega and momentum, energy and momentum, that we're kind of sensitive to. So we're sensitive to frequencies in the 100 kilohertz range and wave vectors in this range of 0.02 inverse nanometers.
Amir?
Yeah.
But in this case, I suppose you could change a lot where the peaks of the filter function is by changing the sequence that you use for.
Correct. Yeah.
You should be able to have like some leeway in operating.
Absolutely. Yes. Yes.
With
Yeah.
pulse, CPMG or things.
That's right. So you're absolutely right. So you can, I mean, this is maybe the simplest version. You could make this filter function be very narrow, and you can select where it is in frequency by choosing more clever pulse sequences. So these are things that we use and play with, but just for the kind of the purpose of demonstration, we're going to use a very simple echo sequence. All right, so before jumping into do we have fluctuations below the spin gap, let me just tell you the material system that we're interested in. So we're interested here in a layered magnet. This is chromium trichloride. And it's actually a monolayer. So it's a monolayer magnet. What's unique about this magnet is that it has very, very small crystalline anisotropy. So the spins want to live in the plane, but they're completely free to orient themselves in the plane, very weak anisotropy. We encapsulate this material between 2 layers of HBN on top and on the bottom. And this is not a scanning experiment, so we place this sample on top of diamond that has an ensemble of NV centers spread all across. And we're basically going to move our light spot to read out what these NV centers are recording as a function of position, with a spatial resolution here that's roughly given by the optical spot, which is on the order of 400 nanometers.
Quick
Yeah.
question. Stuart Parkin reported on some evidence of DKT physics. Like, is it relevant for your experiment? Or
Yes. Yeah. It's probably, so we're seeing the same thing. Basically, we're not going to look at the critical exponent that has to do with how the magnetization depends on temperature, but I'll show measurements of that. It actually allows us to extract some meaningful parameters about this particular system. But yes.
So we should think of it as a basically BKT type of.
Yeah, it's a Heisenberg magnet. Yeah. And I think the interesting there is, I think our motivation for looking into this is because some of the elementary excitations are merons in this system. Perfect. So half skyrmions. As you'll see, I don't think we see evidence of that because these should be suppressed with magnetic field, the presence of merons, and that's not consistent with our observations. But yet we see some other interesting physics that has to do with hydrodynamics that I'll mention. So these are kind of different realizations. The students like to give names to the samples. We're going to be studying pizza.
Sorry, why is it called like that?
I don't know. All right, so again, as I mentioned, measuring magnetization is very hard, or extracting quantitatively magnetization is very hard. What we can do is look at changes in magnetization. The way we're doing it is basically as a function of temperature, we're looking at the magnetic field that the sample is generating. And we assume that that magnetic field at any given position is proportional to the magnetization. So if we write this kind of this magnetic field as a function of temperature, you see that there is a phase transition. The system goes from a paramagnet to a ferromagnet at some temperature roughly in the range of between 12 and 14 degrees. And what this solid line here is a theoretical prediction of what that is, or actually it's a theoretical fit using simple linearized spin wave theory that describes how this magnet is going to melt as you approach the transition, and that allows us to extract the exchange coefficient inside this magnet, which is on the order of 10 Kelvin. So now we're going to use this kind of echo dependence to study fluctuations, and as I mentioned, the fluctuations are in the range of tens of kilohertz. You see what the echo time is, and as the echo time is changing, that is basically also changing our bandwidth a little bit, but nonetheless, the fluctuations are in the range of tens to 100 kilohertz. And the thing that really was surprising to us is note that the rate of relaxation of the NV center actually becomes larger and larger as you lower the temperature. Now, this is very counterintuitive. Typically, you expect fluctuations to diminish as you're lowering temperature, whereas here the physics is fluctuations are increasing. So that's what I'd like to explain. Note also that there is a very, very sharp peak in this relaxation that occurs roughly at the phase transition. This is indeed the phase transition where the system undergoes a transition from the paramagnet to a ferromagnet. And this, again, is a manifestation of fluctuation dissipation theorem. Obviously, at the critical temperature, the system has critical fluctuations. It has very long wavelength fluctuations that match very nicely the distance to our NV. And the frequency of these fluctuations also has some critical behavior. And so this is kind of a very nice way of just imaging the phase transition of a monolayer, which otherwise is quite hard to observe. These are just examples of different locations across the sample showing that it's a very robust effect, this kind of the peak. But actually the focus from now on is not going to be on the peak, but on this increase in relaxation as the system becomes colder. So we already mentioned that these kind of fluctuations, magnons, can only exist above the spin gap. And so these have to do with what's called transverse correlations or flip-flop transitions, where nearby the net magnetization at every given location is constant. I'm basically kind of swapping one spin with another one, but the net magnetization locally is not changing. But you can have something that's very different, and this, Yaroslav, I borrowed from your paper, where the number of magnons is actually changing at a given position. So these are actually longitudinal correlations, and the number of magnons could actually change. And now you could see it's like density fluctuations in air. You can have a region in which you have more magnons than a nearby region, and obviously that will propagate in the form of sound. So as long as these magnons, and I didn't emphasize, but this kind of density fluctuations are a result of magnon-magnon interaction. So whereas these transverse fluctuations are a property of individual magnons, fluctuations in the density of magnons are a property of many magnons. It's the interaction between magnons that drives this. So similar to the electron hydrodynamics, we now have magnon hydrodynamics, where if the interaction rate between magnons is very, very rapid, the system will overall conserve particle number, it will conserve momentum, and it will conserve energy. And that leads to conserved quantity and a sound mode. And very much like in air, the sound speed increases with temperature. So what happens as you increase the temperature, the number of magnons increases, the pressure in the system increases, and so the sound speed increases. And so this is what you would expect the sound mode to be in units of frequency and momentum. And as I mentioned already, what our technique measures is the dissipative component of the response function, the imaginary part of the susceptibility, and that is proportional to the viscosity in the system, which is the interaction between magnons. So maybe not going too much into detail, just to emphasize that this viscosity eventually becomes, so you see that it has a 1 over temperature dependence, namely the system, as you increase temperature, becomes less and less viscous, so the sound mode becomes better and better described as you increase temperature. And on the other hand, as you lower temperature, the decay of the sound mode becomes more robust. And so if I were to compare low temperature to high temperature, what happens is that the sound mode increases, speeds up, and it becomes narrower. So when we look at the fluctuations at very low frequencies and some finite momentum, you see that the decay of the sound mode as probed by this frequency and momentum becomes weaker as we lower the temperature. So we have more and more fluctuations, become stronger. As we lower the temperature, we have more fluctuations because the sound mode becomes slower and it decays faster. This is, by the way, work done with Eugene and Misha at Harvard. And so this is actually a quantitative now measure of this viscosity of the magnon gas. And you see that it fits nicely both in the presence of magnetic field and in the absence of magnetic field. And just to point out what the quantity here is, it's 1 to 2, to the minus 10 in these units. It's actually very, very fluid, very, very viscous, almost comparable to honey. So with this, let me just stop here and see if there are any questions. Thank you. Some new probes to explore the.
Oh, echo, spin echo.
Yes, sound echo. To explore the electrical properties, we then moved to spin properties, and we talked about static magnetization and the challenges in imaging that. And then we talked about some fluctuations in magnets, specifically single magnon excitations that have a well-defined chemical potential, and then magnon-magnon interaction that lead to hydrodynamics. Today, what I'd like to talk about is how can we harness our understanding of spin waves to actually develop yet new and perhaps interesting ways of using spin waves, magnons, to probe quantum matter. So the real first challenge is, can we generate coherent magnons, and can we see them in order to be able to use them for something meaningful? So, in this cartoon, each one of these electrons is generating, has a magnetic moment, generating some magnetic field in space. And as these spin waves propagate, and I emphasize that we're interested in propagating spin waves, not static, not standing waves. These are propagating waves. They have a well-defined wave vector and a well-defined frequency. So if we position our magnetic sensor at just one particular point, what it observes is a time-dependent magnetic field that has a phase. And if that frequency of this time-varying magnetic field is resonant with one of our NV transitions, what this does is it leads to transition. So it starts, if we initialize our NV center in the 0 state, seeing some weak drive at the resonant frequency will slowly process this spin and try to generate Rabi oscillations. But if it's weak enough, then it's just going to lead to a slight change in occupation, which we will see as a change in contrast. So this means that just by observing the contrast of our NV center, we can map in space the amplitude of this propagating wave. But we're also interested in the phase. And it turns out that in the rotating frame of a two-level system, the phase of a drive field dictates around which axis you process. But if we are only looking at the projection onto the z-axis, we won't know around which axis we're processing. We won't have phase information. To get the phase information, what we do is we add another antenna that generates the same time-varying field, but it is position independent. So it's uniform across all space. And so what we have in the rotating frame of the NV, we have our magnon field that has some phase dictated by the wave vector component of this term. And we have a reference signal that is constant, independent of where we are in space. And you see that these two drive fields interfere to give us places in which they would cancel out and places where the strength of this drive will be maximum, and that allows us to extract phase information as well. So this is how a measurement of propagating magnons looks like. This is already with the reference field. So what you can see here are the phase fronts. As I'm emphasizing, these are not standing waves, they're propagating waves. And what we're doing, the reason you're seeing this thing move, is we're basically changing the phase of the reference signal so that we can change the condition in space in which we see maximum or minimum interference. So that's the essence of these. Basically, we're just kind of taking different snapshots of this propagating waves for different phases. So I think this is pretty convincing that we could basically measure propagating spin waves, and we can do it both extract amplitude and phase. And so this is conducive to developing a scattering platform that can use spin waves as the medium to explore matter. So you're all familiar with scattering platforms. The idea is you have something that you shine on an object, and you're looking far away at a screen, and you want to infer the properties of that object from the scattering signal that you have. In a more kind of physical sense, typically we would send coherent waves or particles, for example, neutrons or X-rays. They would impinge on some target and diffract. And the really powerful thing about a scattering platform is that you're not probing the interaction region directly. What you're doing is you're probing something far away where you understand the physics of your particles or waves. They're just in vacuum. And if you have information about amplitude and phase, you can reconstruct a structure factor that tells you how these waves interacted with the material of interest. So the challenge that we kind of presented ourselves with is, can we do this with coherent spin waves? Now, unlike most scattering platforms that use light or electrons or neutrons, these exist in vacuum. Spin waves only exist inside a material. So we need to find our vacuum, which will host our spin waves, and that these spin waves will then interact with the material of interest. So this is what we're envisioning. We have a slab here of some magnetic material. In our experiment, to start with here, it's going to be YIG, yttrium iron garnet. It's a very, very good low dissipation magnetic material that can support the propagation of spin waves over millimeters. We have our antenna that I already showed. This antenna allows us to drive currents, oscillating currents. The frequency of the current will dictate the frequency of the magnons that we're launching. And the dispersion of the medium is then going to pick a particular wavelength that corresponds to that frequency. So this allows us to launch coherent spin waves whose wavefronts are basically parallel to the shape of our antenna. And then downstream, we're going to put some material that sits on top. And again, the motivation in developing this platform is not to replace neutron scattering, for example. It is to basically be able to do experiments in systems where neutron scattering will not be effective. So if I'm interested, for example, in some hybrid system, let's say a superconductor and a ferromagnet, what kind of modes live? What is the property at that interface? This thing will be perhaps useful because it can probe things that are on the monolayer scale and can also probe things whose dimension is in the scale of about a micron or a few microns. So we already saw that in the propagating region here, we have propagating waves. So this is what we can image with our NV center extracting amplitude and phase before we hit our target. Now, we're looking, this image is an amplitude image, no phase information. So this is just recording. There is no reference antenna applied here. So this is just the amplitude. You see that the interaction region here, the sample is this white circle, and I didn't mention what it is. It's actually another ferromagnet. It's permalloy. It has a very different Curie temperature, a very different spin wave spectrum than our vacuum, which is YIG. And you see a very complex response in the vicinity of the sample, but we're not going to analyze that. We're going to look far away where things become simple. They're kind of diverging as you'd expect at constant angles. The physics is more or less the same. And this is the amplitude image. And then if we turn on our reference signal, we can extract phase information. Again, very complicated behavior near the target, but far away, things begin to become kind of more or less standard. And the procedure we're trying to follow is to look only at the portion far away, and by inverse Fourier transforming basically what we see based on the amplitude and phase to say something about the structure factor. Because this talk is really more about the techniques than about the science, I'm not going to go in depth into what it is that this method is measuring, but just to show you that we're seeing something that's less, kind of not very consistent with what we expect. So what do we expect? So it turns out if you analyze what this scattering process is expected to give to you, assuming the interaction between your spin waves and the target is the exchange interaction, then if the target is just a magnet who's magnetized in some direction and its magnetization is uniform, it turns out that what scatters the spin waves are gradients of this magnetization in the direction of propagation of the magnons. So what we expect to see when we kind of figure out what our target is, what scattered our spin wave, is we expect to see a strong signal up on top, a strong negative signal at the bottom, because that's the only place where the magnetization is changing. It's due to the boundaries of the magnet. But what in fact we find is that the entire disk is generating the signal that scatters the spin waves, and this is something that we don't really understand very well yet. Now, part of the reason we don't understand it has to do with the fact that the physics that connects between what we measure and what we're trying to report is not yet well understood for us. So this is an example where we don't really understand well our measurement technique. And it's going to take some time to figure it out. And the reason is that there are many coupling mechanisms. There could be an exchange coupling, which is what we've analyzed, but there could be also dipolar interaction between the moments in the target and the spin waves. There could be galvanic, namely the spin waves are generating time-varying magnetic fields. These are generating currents in our target, and these are then scattering. The currents are generating themselves magnetic fields that scatter the spin waves, et cetera, et cetera. They're inelastic processes as well as elastic processes. So this problem is very complex, and it's going to keep us busy for quite some time. So up to now, I talked about spin waves and the use of spin waves in magnetic systems where we expect to have spin waves. But are there other systems in which we have magnetic phenomena, and can we figure out ways to explore them and harness their properties. In the introduction, I don't know if you remember, but I presented some challenges, for example, the measurement of spin currents or the detection of antiferromagnetic order in a layered material like graphene. This is actually an expected phase, a canted antiferromagnetic phase that occurs at a very strong magnetic field deep in the quantum Hall regime. This is a magnet, but we really don't have that good of techniques, or at least we didn't, to probe its magnetic properties. Typically in quantum Hall system, the way you probe the system is by electrical transport. These spin structures and their excitations do not couple to charge, they're neutral, so that presents a challenge. And I remember having a conversation with Yaroslav almost a decade ago about this problem, which led to some very nice constructions and ideas of how to probe spin waves inside these systems in the quantum Hall state, and actually really opened up a nice new area of exploration for us. So I'd like to start by just reminding everybody why a quantum Hall system actually behaves like a ferromagnet. So if we take graphene, it doesn't have to be graphene, but it has linear dispersion at zero magnetic field. You apply a magnetic field, you get Landau levels. There are two quantum numbers in graphene, spin and valley. And so each one of these orbital Landau levels is fourfold degenerate. So here is kind of a zoom in on the fourfold degenerate. Each one of these Landau levels corresponds to a different spin and different valley combination. Now we can ask, well, what happens if we try to fill up this Landau level? So I'm trying to fill out the orbital, the n equals 0 orbital Landau level, but I want to fill it up only a quarter of the way. So I could do it in a democratic way by filling kind of, just a portion in each one of the different flavors. So each flavor gets the attention it deserves. But of course, this is not what nature wants, and very much in the spirit of ferromagnetism, what the system would prefer is to fill up entirely one of these 4 Landau levels. We gain exchange interaction by doing that and leaving the other 3 empty. This is what's called a quantum Hall ferromagnet, because this lowest Landau level, because we have a magnetic field, will be spin polarized and will basically be a very good ferromagnet. But in fact, it's a very, very weak ferromagnet. The demagnetization fields that exist in normal magnets, in this case, is going to be 0 because magnetization density is so small. So it's actually quite a simple magnet where the spin gap in this system for magnon excitation is just going to be the Baer-Zeeman energy. So this is the filling factor 1 out of 4 here. It's a ferromagnet. The same happens when you fill 3 out of the 4. When you fill out 2 out of the 4, this is this canted antiferromagnetic phase that I mentioned, which is even harder to detect because at least the ferromagnet, you could say, well, it's generating some magnetic fields. Maybe I can detect them. The antiferromagnet is generating weak magnetic fields because it's only canting, so it's harder. But I want to emphasize that these are actually quite remarkable magnetic states. First of all, they're electrical tunable. So in this system, I could just change the density and go from ferromagnet to antiferromagnet. This is quite unique. You don't have magnetic systems that you can do that. And the second is, in terms of the lifetime of the spin excitations in these systems, they're expected to be very long because graphene has very weak spin-orbit interactions. So this is maybe a good candidate to study spin chemical potential, spin superfluidity, which was the paper that Yaroslav wrote, and then also maybe spin hydrodynamics that I mentioned already. So where are the challenges? So already almost more than 20 years ago, Physics Today of 2000, Steve Gervin, who was then very active in the field of quantum Hall physics, wrote a review paper about spin and isospin. Isospin means the other degrees of freedom, and just similar to the spin ferromagnetism, you can have valley ferromagnetism. So any order, any quantum variable intrinsic degree of freedom could lead to an ordered state. But he writes that at filling factor 1, spin waves are the lowest energy excitations. but because they do not carry charge, they do not have a large impact on the electrical transport properties. So this was a big challenge for many, many years, but somehow we stumbled upon a way to overcome that. I'd like to tell you a little bit about that and see where that has led us in the study of magnetic phases of 2D systems. So here's a depiction of a quantum Hall ferromagnet. So this system is a 2D system subject to a strong magnetic field, and we're at filling factor 1, where we know that all the spins are pointing along the direction of magnetic field. We explicitly broke time reversal symmetry, etc. We have 2 contacts, and we're going to study transport in the conventional way. So we apply a bias from one side to the other, and we know that the bulk is gapped for charge. It's not gapped, so it is gapped for spin excitation, and the energy gap, as I mentioned, is just the Zeeman energy. No exchange goes into the spin wave excitations of this ferromagnet. So when we send current, what happens is that the chemical potential of this edge becomes high, mu, and the chemical potential of this edge becomes 0. So there's an imbalance in the chemical potential. This is what leads to the quantization of conductance, the way we understand it based on transport. Let's make it a little bit more complex. Let's increase the density near the contact so that the filling factor near the contact is actually filling factor 2. This is not hard to do. You could basically just deposit gates in a way that you control the density separately near the contact versus the bulk. So we have a system schematically shown here. This is filling factor 2, which is this configuration, has all 4 flavors filled, so it's a non-magnetic state. There's nothing magnetic in that state. It's kind of an uninteresting phase, but it has 2 edge modes. One edge mode is a spin-up edge mode, corresponding to this state. The inner one is the spin down, opposing the external magnetic field. So now let's look at what happens under bias. So as I mentioned, this chemical potential here, the edge states that emanate from the left have a large chemical potential because of the bias that I apply, and the one emanating from the right have a low chemical potential. So if you look at this corner here, we see that there are 2 edge states that come together. One of them has a high chemical potential, the spin down one, and the other one, the spin up one, has a low chemical potential. And in principle, this is out of equilibrium, so the system might look for ways in which electrons from one edge state could scatter into the other, but you need to satisfy energy, momentum, and angular momentum. So all these things need to be satisfied, and it turns out that it's rather high to do because there's no spin-orbit interaction in the system. So it turns out that these processes, even though available, there are a finite density of states that are available, they're not going to happen until you exceed the spin gap in the system. Once you exceed the spin gap in the system, you can resolve the issue of angular momentum conservation because you can have an electron flip its spin, thereby launching a magnon into the system. So below the magnon gap, which is just bare Zeeman, even though strong exchange exists, the spin wave excitation, the lowest energy is just the bare Zeeman energy, which is really our telltale that this is the physics that goes on here. But once you exceed the magnon gap, so chemical potential above the Zeeman energy, you can have a spin flip and thereby launching a magnon in the bulk. Now, hey, this might be a nice picture, and if we're just launching magnons into the bulk, we're not going to know that this process happens because what happens is we're just redistributing charge between these 2 edge states. We're taking charge from the inner one, putting it at the outer one, but it's still flowing in the same direction. So conductance is not going to be affected. In order for conductance to be affected, these magnons that are launched in the bulk need to be absorbed somewhere and change the way current is distributed across the device. And there are 2 places where they could be absorbed that makes a difference. If they get absorbed here, again, nothing happens because these are all inwards. The only place that matters if they get absorbed is here and here. So if they get absorbed here, what happens is that we're going to take charge from the outer channel and put it in the inner one. So we're going to reduce the current. So our conductance is going to decrease. And if we we absorb magnons on this corner, we're going to get less back current, so we're going to get an increase in conductance. All right, so this is basically the scheme. And note that these two processes compete. So one increases the conductance, the other one decreases the conductance. I didn't mention, but depending on the sign of the bias, where we actually launch magnons also changes in this device. So for negative bias, it's launched at this corner. From positive biases, it's going to be launched from this corner. But nonetheless, if we can see the change in conductance, then we know that that's exactly what's happening. And this is what you see right here. So near zero bias, you have well-defined quantized conductance of E squared over H. And once you hit the bare Zeeman energy, no exchange, you see a drop in conductance for both positive and negative bias. Yeah?
It looks like it remains somewhat quantized after dropping.
It's not. You'll see it in a minute. So it's actually what happens beyond the onset of magnon generation, something we understand very little about. So first thing we need to do when you discover something that you kind of think you understand is to check consistency. So you want to see if our picture really holds. And so I mentioned this competition between increasing and decreasing, and that's really geometric. It's where the magnons get absorbed, so you can design geometries where the conductance actually increase on the two biases. You can design a geometry where the conductance decreases when you get to Zeeman, and you can design geometries where it will increase on one side, decrease on the other side. So this was kind of a very good indicator for us that we understand how magnons are absorbed in this system. So now we can go one step beyond. Okay, so we have a mechanism of generating magnons. We know where they're absorbed. So we can use these two left contacts here just as we did before. So magnons are going to be generated, and we can monitor the conductance between these contacts, and that has to do with how magnons get absorbed in the various corners here. But now we can have additional contacts. And normally in a quantum Hall system, any two contacts that sit along a quantized Hall edge, you're not going to get any voltage difference because the rho XX, the longitudinal resistance in the system, is zero. But if magnons are kind of freely propagating through the bulk, and this is the key difference here, these excitations are bulk excitations where anything charged here is along the edge. We're charge gapped. If these kind of neutral excitations get absorbed near the contacts of these non-local probes, then you're going to get a voltage despite the fact that you're in a quantum Hall regime. So this is what we've designed to do. So here is an experiment which now basically kind of develops a scattering platform analogous to what I did with the magnons in YIG. Now we're trying to develop a magnon scattering platform where we launch magnons on one side, we try to detect them somewhere else, and we want to see how they pass through interesting phases of the material. So we have some targets. So in this device, we have our 2D system. It's all in the nu equals 1 region, so it can support magnons everywhere. But in the middle here, we're going to have some gate that we can change the phase that we are exploring, and we're going to go from ferromagnetic phase maybe to the antiferromagnetic phase to non-magnetic phase, and we'll see what happens. So first off, let's look at the conductance, right? So this is kind of not invoking any of these non-local probes. We're basically kind of applying a bias between these two contacts and measuring the conductance. The density that we're changing is somewhere far away from these two contacts. And you see that the conductance is quantized at zero bias. This is the bias axis. Once you reach the dashed lines, that's the Zeeman energy, bare Zeeman. Sudden drop in conductance. We know magnons are being launched in the system anywhere beyond this bias, but nothing really depends on the density or the phase in this region, because this is all kind of a local process. It involves magnon absorption and generation near the contacts that are being used. But now let's see what happens on the other side of this region here. So that's the non-local signal. Just to orient you in terms of what are the phases that are being explored as a function of this gate voltage, I've drawn lines here. So basically, This region here is a filling factor of -2, so it's a non-magnetic phase. Filling factor 2 here is the non-magnetic phase. Nu equals 1 is a ferromagnetic phase identical to the one we generate the magnons in. Nu equals -1 is also a ferromagnetic phase, but very different from the one we generate the magnons in. This is nu equals 1, this is nu equals -1. There are actually a lot of edge states that need to separate between these two phases. And the middle here is the nu equals 0, where we expect the canted antiferromagnet to live. Okay, so these are the 4 phases that we're exploring in this region, and what we want to see is how magnons traverse these regions, telling us something about the magnetic order of these various phases. So this is the non-local signal. Again, you see that there is no non-local signal below the Zeeman energy. And that's okay, because we're just not generating, our source is 0. We have no magnons sourced, so there's nothing to explore. Once we exceed, we see that there is a very strong change in the non-local signal, and when we, for example, look at filling factor 1 here, then our plane becomes completely uniform. It's just one ferromagnet. We're launching the magnons here. They arrive at the non-local signal, and we see their signature. And the fact that it's changing sign is exactly consistent with the geometry. Increase in conductance in one side, decrease in the other side has to do with geometric factors. When we look at filling factor 2, we see a very weak signal. We expect no signal whatsoever because this region is expected to now block the propagation of any magnons. This region cannot support any spin excitations. We believe that the weak signal that we're seeing has to do with some leakage of edge currents that are actually going at the boundaries. Remember, at the boundaries, we need to go from filling factor 2 to 0, which means there is a very sliver of filling factor 1 near the boundary that could leak some signal across. So the first surprise is what happens at filling factor -1. Filling factor -1 is a ferromagnet, and you see that magnons are completely unimpeded. So the fact that you're going from filling factor 1 to -1 to 1, for neutral excitations, don't care at all. So this is very nice. The exchange interaction somehow, when we have a microscopic picture, I'm not going to go into it, allows these magnons to kind of very freely continue through, despite the fact that you have, edge channels that live at this boundary and at this boundary. None of that matters. It's really all the bulk exchange interaction that allows you these spin waves to propagate. And the second surprise is that this is the canted antiferromagnetic phase, and we see very weak signal here. So we were puzzled about that. But then once you look at a larger bias scale, you see that indeed you can generate spin wave propagation through the canted antiferromagnetic state. And the reason it has this kind of large energy required is exactly the same physics that you encounter in magnets when you couple two different magnets or an antiferromagnet with a ferromagnet. Basically, it's exchange biasing. So there are barriers that are created between the ferromagnet and the antiferromagnet that we need to overcome. These are exchange barriers in order to be able to propagate magnons through the canted antiferromagnetic region. All right. So now that we have kind of a new platform that we can launch magnons, see what happens as they propagate through various phases, we'd like to take it one step further, and we understand the physics of what scatters magnons and what doesn't scatter magnons. I would ask, can we actually image where magnons are propagating across this sample? So really, what is the microscopics? Because up to now, we're just kind of detecting non-local signals, but we don't really know where the magnons are propagating. And are they really being generated one corner, detected at the other corner, etc.?
Can I ask it?
Of course.
Why is the boundary, let's say, between these phases not so sharp?
Between the canted antiferromagnetic phase and...
Yeah, like I would maybe expect that the blue sort of is like a rectangle, right? Here it's sort of like elongated shape. Slowly
Right. So remember, when I talk about the phases that exist in the system, filling factor 1, filling factor 0, there is always a finite range in which the system undergoes a transition from one phase to the other. And in space, what this means is you have regions in the system which is one phase and the other. It's like a two-component percolation transition. So we believe that is what kind of blurs the system. You can have coexistence of different phases as you're transitioning from one to the other. So I want to remind you of a technique that was developed by Bob Westervelt at Harvard many, many years ago, and it's a scanning gate microscope. So what he envisioned, and actually carried out beautiful experiment, is a device where you can send current through the device. You can have maybe a constriction here, something that impedes the flow of current. And then what you do is you bring a gate, you bring a needle, and the needle can change the potential locally. And if you if you create a potential barrier that's strong enough, it's going to scatter electrons. And what's going to happen is that if you perturb the electron flow in places where electrons are actually flowing, you'll see a change in the resistance. So what they were monitoring is basically the conductance across this constriction, this point contact, as a function of the position of the tip. And the idea is that what the tip is doing, it's scattering electrons. It's forming a barrier that the electrons cannot penetrate. And what they saw is indeed, very beautiful coherent signals, right? Where when the tip is sitting here, what happens is that charge that is trying to go through the constriction gets reflected back by the tip, and therefore the conductance decreases. But there are some interesting standing waves that occur, etc. So it's a non-local way of probing where current is actually flowing in this device. And we were kind of inspired by this, and we're thinking, well, can we do the same thing now with magnons? So we think magnons are flowing through the bulk. We know that if we change the density, let's say with a tip, to go from filling factor 1 to filling factor 2, filling factor 2 is a barrier for magnons. Will we be able to see how magnon flow is impeded as we're moving around this barrier? So to implement this, we are using a tip that is actually more sophisticated than just a metal tip. It's not just a gate, it's actually a single electron transistor. I'll mention its use later, but for now, let's just think of it as a gate. It allows us to image very nicely the boundaries of the sample, which are shown here. And this is kind of an optical image, and we're going to be imaging this kind of small square. And the experiment is very simple, right? So we're launching magnons, let's say, between these two contacts, and we're seeing, with our tip, we're going to see, okay, when does the conductance change depending on where the tip is, which tells us exactly if magnons are flowing there or not. If magnons are not there, changing the potential there is not going to make any difference. Yeah?
What kind of potential does the tip create? Is it electric potential?
Yeah, it's electric potential. So remember, right, oops, I'm going the wrong way, sorry. So remember, so the different phases that I'm talking about here are all different simply by the density in this region. So when this region is at nu equals 1, it supports magnons. But if I change the density there, electrical density, to be at filling factor 2, magnons can't propagate. And you see they're not propagating. So changing the electrical potential changes the local phase, and that phase will either support magnons or not. We're taking advantage of the fact that we can change the density to a phase that does not support magnons, creates a barrier for magnons. Okay, so here are some experimental results. These are all unpublished, but will take us time to kind of really know exactly what we're doing. But you see that when the bias is below the Zeeman, so no magnons are generated, as we're scanning our tip, even though there is conductance in the system, the conductance is not changing at all, irrespective of where the tip is. But now once we apply, let's say, a negative bias or a positive bias, and as I mentioned, that changes where the magnons are generated. For negative bias, they're generated up here. Positive bias, they're generated down there. You see that we are starting to get contrast. And this contrast is, to some degree, consistent with where we think magnons should flow and be absorbed or be generated. So these are these color contrasts. So this is kind of the first image of magnon flow in a 2D system. I want to point out that you have these kind of ring-shaped objects, and if you look at a cross-section in density, so if you change the density near that region, what you find is that you actually have many of these rings. So this is kind of a density cross-section of the signal in this region, and you see a lot of kind of interesting physics. And without, again, going into detail, what this is telling us is that the absorption and generation of magnons is aided by impurities. I don't know if you remember some beautiful images coming from Weizmann Institute on thermal transport and graphene, showing how heat is generated in the quantum Hall regime along the boundaries, again showing always heat generation, phonon absorption, which is aided by the presence of impurities. Similar physics is happening here. This is the process of magnon generation and absorption, requires impurities. This is not entirely unexpected because remember, the scattering of magnons, scattering of spins between the two edge channels satisfies angular momentum because we're flipping a spin and we're generating a magnon, but you also need to satisfy conservation of linear momentum. And impurities help with that. This is a non-local geometry where now we're kind of sending current, launching magnons far, far away, and we're still imaging the bottom part. And again, you see this kind of impurity-aided absorption of magnons near the contacts where we expect that. Yeah?
How do you realize the phase transition in this device by the backgate control? Or?
Yes. So backgate controls the uniform density, but the tip controls the local density. So if the tip was unbiased, obviously as we scan it around, we're not going to see anything because our tip is not going to, we're not creating a perturbation for magnon flow. But once we bias it, we move away from the filling factor that supports magnons, we're scattering magnons, and that's the contrast that we're seeing. So the tip is what impedes the propagation of magnons, and this is what we're trying to image. Yeah?
It seems like even if you have the tip outside of your sample, you're impeding magnons. Can you comment on that?
Yeah. So remember, the tip is exerting a bias. That potential is not local, right? It changes with some distance. So the further away the tip, we're still going to be gating an impurity that sits somewhere here, even though the tip is outside. So you see that there is kind of the ring shape is because there is a geometric condition under which along all this contour here, for example, the change in potential at one particular point is all the same. Yeah?
I just want to make sure I understand the plot. So this is, you're applying voltage between, let's call them contacts 1 and 2 on the top right, for instance, and then you measure the change in the conductance between contacts 3 and 4 as a function of the location of the tip.
You're measuring the voltage difference.
As you apply current, I mean.
So you're driving current between these two contacts, and that has some conductance. It's quantized below the Zeeman energy, and it's below quantized above. That launches magnons in this sheet all around the bulk. Some of these magnons get absorbed between these two contacts. So we're also measuring the voltage difference, the potential difference between these two contacts. If you're in a quantized Hall system, that would be 0. But if magnons are being absorbed, it turns out that will change that condition. And this is the plot here, the non-local voltage that you measure between these two contacts due to magnons generated up here.
And then each point in space, as you move the tip around,
is the tip position.
The voltage somewhere else.
Exactly. So there's a lot that we don't understand here, but I'm not going to go into that. I just want to say that there's even more than we can do. I mentioned that these tips are single electron transistors, so they allow us to measure the energy gap in the system, in addition to just be gate. So we can use them in different modalities. And one thing that's very interesting is that the presence of magnons can bind to electrons to form skyrmions. And the formation of skyrmions will alter the change in chemical potential as we transition from one quantum Hall phase to another. And I'm not going to go into detail, just to say that, again, this kind of local technique allows us, very similar to what I've talked about in YIG, we can actually measure the chemical potential of spins, of the magnons in the system, as a function of our bias. So as we're generating more and more magnons, we can extract precisely what the chemical potential is. And you see that it's actually approaching quite fast the Baer-Zeeman gap, at which point we would expect to see some superfluidity. We could also extract the number of spins that are associated with these magnon-free electron-bound entities that are skyrmions, and what is the average spin in these skyrmions, and you see that we can get here up to roughly three spin flips per charged excitation. So I'm kind of at the end here. I want to also say that now that we understand this platform, we could try to apply it to really systems that have very rich set of phases. So you know about twisted materials. So here we're envisioning a situation where we have one sheet of graphene, big, that supports our magnons, but then in our scattering region we have a twisted set of layers that can support really a whole range of phases, including fractional churn insulators and many, many interesting creatures. And the only thing we know about these phases is through charge transport. Here we're hoping to get some nice information about the underlying spin conductivity or spin degree of freedom. All right, so this brings me kind of to the conclusion. So I think I've pounded this notion of using known physics to connect between measurement quantities and quantities that we want to report. I want to kind of also emphasize here the important role of new discoveries. When you have a new discovery, you could first of all ask, what can I use it for in terms of developing new measurement techniques? And that could both be in the form of new quantities that we can measure or new physics that we can use to report interesting quantities. And so with this, just to thank the group for doing all this work and see if you have any questions. Thank you.